Some of the advantages of using EFI rather than mechanical means of supplying fuel and spark to the engine really come to fruition after you've mapped the engine. Things like closed-loop oxygen sensing, knock control, and individual cylinder corrections can be done on the fly in real time by the ECU. Let's take a look at each one and see what we can learn. When we talk about closed-loop control, we simply mean that we are taking the information that the oxygen sensor is giving us and using it as part of a calculation on the next engine cycle. So here is the difference between open loop and closed loop. When the ECU is in open loop, it makes an assumption that the values that the tuners put into the tables are correct. If there's a tuning error or a calculation error, nothing is done about it. When operating in closed loop, the ECU pays attention to what the oxygen sensor is reading. For example, let's say the day you mapped the engine on the dyno, it had a target air-fuel ratio of 13:1. You've put the numbers in the base fuel table on that day, and on those conditions, you got an air-fuel ratio of 13:1. But for various reasons, as the vehicle's been operated in real life, some of the conditions have changed, and there's a slight amount of error. Maybe now we're running at 13.3:1 instead of the target of 13:1. In open loop, that error would simply be ignored. But in closed loop, the oxygen sensor will be relaying that error to the ECU, and after the ECU has done its calibrations, it would then make a correction based on the amount of error. This adds a lot of flexibility and performance to the tuner's ability to make the engine run well at all times, not just on a single day under a single set of conditions. If we think about it like this, when the vehicle's tuned properly and the closed loop system is operating, there's very little need for the user to connect to the laptop and make tuning changes. Consider the vehicle that you drive to work every day. Do you really need to keep a laptop in the back seat just in case? Not typically. And your aftermarket ECU can behave in exactly the same way. Let's take a look at knock control. Knock control is also one of the systems that can be used in open or closed loop. But to do knock control, we need a knock sensor. This is normally some sort of piezoelectric microphone that attaches to the engine and listens for a specific range of frequencies or noise that the engine makes during abnormal combustion events. When these events occur, the ECU detects the unique noise coming from the sensor and records a knock event. Whether or not the ECU decides to do anything about it depends on whether you've selected an open or closed loop knock control strategy. If we're in closed loop, the knock control system will adjust the ignition timing to try and contain or eliminate the amount of knock that's occurring. So for example, you've tuned the engine on the dyno and everything was great. But when you deliver the car to the customer, or it might be your own car, you find yourself with a tank of low octane fuel, much lower octane than what the engine was tuned on. Suddenly, the engine starts to experience a small amount of knock. In open loop, the engine would continue to knock until that whole tank of fuel was used. But using a closed loop strategy, the ECU would adjust the ignition timing signals on its own and avoid the detonation and engine damage. Something that a simple mistake like buying the wrong fuel could have caused. Now, consider an engine that has trouble with the distribution of air and fuel mixtures between each individual cylinder. A common example of this is a V8 engine with an intake manifold joined to a carburetor. It's fairly common knowledge that not all of the cylinders will have the same air to fuel ratio. Optimizing each cylinder's air and fuel ratio can provide benefits to both economy and performance. With an ECU, because we're controlling each fuel injector individually, we can actually treat this V8 engine as 8 single-cylinder engines, and we can choose the amount of fuel delivered or the pulse width to each injector to optimise the cylinder. You could even, for example, have a different kind of injector in any cylinder you want, and the ECU could simply run the program, understand the changes, and compensate for that mathematically. It would then deliver the correct amount of fuel to each cylinder. Same thing goes for the ignition system. If you have a particular cylinder that you've been measuring a higher or lower exhaust gas temperature than the rest, you can change the ignition timing not for the whole engine, but for each individual cylinder. Let's take an example. Let's say we have a high performance V8 that makes 800 horsepower. Theoretically, that means that each of the 8 cylinders makes 100 horsepower. But the reality is, most engines are never that equal. Some cylinders could be making 90 horsepower and others could be making 110. Because we have the ability to optimise every cylinder's ignition timing, we can add or subtract timing per cylinder in order to get the best results across the whole engine. This is a strategy a lot of high-level racing teams employ that simply wouldn't be possible without the advent of electronic engine controls. For these and many other reasons, things like boost control, drive-by-wire throttle control, traction control, variable cam control and countless others, the EFI system and the ECU that's controlling the system offers tremendous advantages over previous methods like carburetors and distributors. We really hope that you've enjoyed this introductory video, and we hope now that you're confident to get started in the world of EFI tuning using fuel injection.